This section is about inverse functions. First, I want to introduce a new definition. It's called one-to-one function. One-to-one function is a function that for each input, there's exactly one output, and for each output, there's exactly one input. Say we have a function f, and this is the domain, and this is the range. And say the domain has 1, 2, 3, and the range is ABC. And if 1 is mapped to A, 2 is mapped to B, and 3 is mapped to C, this function f, for each input, there's exactly one output, and for each output, there's exactly one input. And this function f is a one-to-one function. When a function is not a one-to-one function, if you look at this case, this is your domain, this is your range, and you have 1 and 2 in the domain. 1 is mapped to, let's say, 5, and 2 is also mapped to 5. And this is a function because for each input there's exactly one output, but it is not a one-to-one function because for each output there's not exactly one input, there are two inputs here. Okay, how about this case? You have x and y, domain and the range, and for the input you have, let's say, 3, and this is mapped to both 5 and 6 in the output. This relation is not even a function, so let alone a one-to-one function. For relation to be a one-to-one function, you need to be a function first. Then you can be a one-to-one function. Here we have a function f with several ordered pairs. My question is f a function? If it is it a one-to-one function? You can pause the video to test yourself, and I'm going to review the answer now. First of all, this relation is a function because you don't have any repeating x values. All the x values are different. That means for each x, there is a corresponding y value. But check over here, for the first order pair and the last order pair, both the input 2 and 6 are mapped to 3. That makes this function not a one-to-one function. Now, how do we decide if a graph represents a one-to-one function? Say I have a straight line like that, and I want to know if this graph represents a one-to-one function. First of all, it needs to be a function, right? So to be a function, the graph needs to pass the vertical line test. Does it pass the vertical line test? Yes. So if we run a vertical line through the graph, and we will see at anywhere the line will intersect the graph for at most one point. That means it's a function. After we decide the graph is a function, we can use a similar test. It's called the horizontal line test to decide if it is a one-to-one function. The horizontal line test is pretty similar to the vertical line test. You will run a horizontal line through the graph, and at anywhere, if the horizontal line is intersecting the graph for more than one point, then it is not a one-to-one, but it is intersecting the graph for at most one point at anywhere. That means it is a one-to-one function. So in this case, it does pass the horizontal line test. So not only it's a function, it's a one-to-one function. That means for each input, there's exactly one output, and for each output, there's exactly one input. So to decide if a graph is a one-to-one function, you need to pass both vertical line test and the horizontal line test. For example, here we have a parabola. So I want to know if this graph represents a one-to-one function. First, we will test if the graph is a function by using the vertical line test. So if you run a vertical line through the graph, you will find out it's actually passed the vertical line test. So it is a function. So after we know it's a function, we will run the horizontal line test, and the graph doesn't pass a horizontal line test, because you can see for this horizontal line, it's intersecting the graph on 2 points, right? So it is a function, but not one-to-one. Now let's look at this graph. Is it a one-to-one function? Okay, if you just test it on the horizontal line test, it does pass the horizontal line test, but it's actually not a one-to-one function because it doesn't pass the vertical line test. So it is not even a function because it doesn't pass the vertical line test. So not a function, let alone a one-to-one function. Now that we know what a one-to-one function is, we want to introduce the concept of an inverse function. Actually, only a one-to-one function can have an inverse function. Say we have a function f that maps 1 to a, 2 to b, and 3 to c, and the inverse of f is a function. We use the symbol like this, f to the -1 is actually the inverse of f. Well, the inverse f is a function such that it maps a to 1, b to 2, and c to 3. So it is a function that switches the input and the output of function f. That is the inverse function of f. And you can see here the domain of a function f is actually equal to the range of the inverse of f. And similarly, the range of the function f is the same as the domain of the inverse of f. So we can see here, since f1 is equal to a, and we can get the conclusion that for the inverse of f, it will map a to 1. Here's one example. If we have a function f of x equals x plus 5, and f of -3 could be found as -3 plus 5 equals 2, right? So f of -3 is equal to 2. So from here, we can find that the inverse of f of 2 should be equal to -3, because the inverse of f is a function that maps the output of f into the corresponding input of f. Now let's say we're given a function, let's say g of x. It is 2x plus 5, for example. And let's graph g of x really quick. Okay, it is a function with y-intercept of 5. So let's say this is 5. And the slope is 2, so go up 2 over 1. And connect those 2 points, we have the graph of g of x. The 2 points on the graph we found was 0, 5, and this point looks like that's 1, 7. Right, those are the 2 points on the graph. Okay, so from here we can make a conclusion that since 0, 5 is on G, that means 5, 0 will be on the inverse of G. Similarly, 7, 1 will be also a point on the graph of the inverse of G. So let's plot these 2 points. So 5, 0 will be, let's say, somewhere here. This is 5, 0. And the other point is 7, 1. So 7, 1 looks like this point. If we connect these 2 points, we have something like this. I know I don't have the most accurate graphs here, but the 2 graphs are actually symmetrical along the line y equals x. So that means if you fold this coordinate plane along the line y equals x, the 2 graphs should overlap. This actually works for all inverse functions. If you have 2 inverse functions, f and the inverse f, then their graphs are symmetrical along the line y equals x. For example, here I give you 4 graphs, and for each graph I want you to graph the inverse of f. Starting from the first graph. First of all, the function f, it looks like it passes through 3, 0, and looks like it's past this point, which is 4, 1. Right. So the inverse function should pass 0, 3, which is right here, and 1, 4, which is right here. And notice that the 2 graphs should be symmetrical along this line. Y equals x. So the graph would look like this. And this should be a rough graph of the inverse of f. Okay, similar for number 44, for the second graph. Okay, so since f passes 3, 0, and this point is 0, 4, so the inverse of f should pass 0, 3, which is right here, and 4, 0, which is right here. And since the 2 graphs will be symmetrical along the line y equals x, which is this line, and your graph for f inverse should look like this. This is the graph of the inverse of f. Okay, similar for the next graph. First of all, since it passes 0, 0, the inverse should also pass 0, 0. And it looks like this point is negative 1, 2. So the inverse function should pass 2, negative 1, which is this point. It looks like it's a straight line, so the inverse function should also be a straight line. So it should look like this. That's the inverse function of f, and you can tell the 2 graphs are symmetrical along the line y equals x. Now the last one, first the function passed 0, 0. That means the inverse function should also pass 0, 0. And then another point function f is passing is 1, 3. So that means the inverse will pass 3, 1, which is here. So connect 0, 0 and 3, 1. You should have the graph of the inverse function of f. So it's also a straight line.